real soon. Hi, welcome to the next lecture of Introductory Astronomy. Today we have two what is this. This is during the lecture. I decided to test out my lecture and run this. So this will be coming up during the lecture, and you get to guess what is this strange movie here. But the original one I had set up was this one. So you can also wonder what this is. And so today we're going to go back into the earliest parts of the universe and talk about the universe as a whole and get into some of the latest speculations about what's going on and what is this universe that we live in and how did it start. We're going to go back to the Big Bang again and go through it with a little bit of a different eye. And this strange image might have something to do with the early universe. And of course, it might also have something to do with mayonnaise. All right. So, in case you were wondering, this is Physics 1600, Introductory Astronomy, being taught at Michigan Tech. This is an actual course. These are not actors. These are real students in the studio audience here. And assuming they take all the quizzes and final and midterm and do reasonably well, they'll be getting actual credit. But if you're at home and you're not involved in Michigan Tech, you can go through all the lectures on iTunes and elsewhere and see all the lectures. But I can't let you in to see the quizzes, though. I get usually an email about that a week or so. So I can't do that. Today we're going to be talking a lot about the early forces in the universe and inflation. And next time we're going to be talking about life in the universe. Next time will be the second to last lecture. And then the last lecture, both of which will be occurring next week, will be pseudoscience. So I am Robert Nemiroff. I am one of the main people involved in creating the Astronomy Picture of the Day web pages, which are an important part of this course. You'll see APOD images every lecture. And we'll be reviewing a whole bunch of APODs today because we were off for a break. This class will also end earlier than usual because there will be reviews today, class reviews. So I want to give the class time to do that. So if you're logged into the course, if you want credit for the course, you need to go to courses.mtu.edu. And if you're just learning that now, there's little hope. So lecture material in Wikipedia, there is no book. Don't worry about the higher math, particularly here at the end, because a lot of people can apply some higher math to string theory, cosmology, things like that. Don't worry about it. We're interested in the basic math and the concepts here. You need to read and understand the astronomy pictures of the day posted during the semester, right up until the last lecture next week. You should have completed the quizzes. There will be a quiz released later today and due next week. And the final will be released a week from today. The way this course is running in the fall of 2008, it will be released on 12/10 and due a week later, the next Wednesday, 12/17. If this class is going to be rebroadcast in the spring or the summer, then those dates will be changed. So we'll just put in the dates that your instructor is telling you. So the Wikipedia entries today to look up fundamental interaction, which is what you get if you look up fundamental forces on Wikipedia. Cosmic inflation, dark energy, multiverse, whatever that is, and anthropic principles. There'll be some strange stuff going down today. Fun to think about, not always testable. So this is a review from last time. Now we're going to go through the early universe again, but here it is in slide form. So far as we can tell, way back at the Planck time, 10 to the minus 43 seconds after an extrapolated beginning, which we don't really know exists, there were quantum fluctuations that somehow led to a period that we'll talk more about today called inflation. Inflation in the universe expanded exponentially, where parts of it actually went faster than the speed of light compared to other parts. So the first question people get is, how can that be? How can things go faster than the speed of light? And the answer to that is that special relativity created by Albert Einstein in 1905 doesn't involve gravity, it just involves things moving around. That says nothing can move faster than the speed of light. In particular, what he means by that is locally. So if something is right with you, right next to you, or passes by you, you can never measure that, assuming that there is infinitesimal distance between you and it, greater than c, the speed that light goes. And even then, light itself is just an ideal. neutrinos essentially move at the speed of light. Other elementary particles essentially move at the speed of light. So the speed of light is the fastest possible limit you can go. It might be one day that we find out that some light moves faster than others, but so far as we can tell right now, in a vacuum, they move the same. After this inflation, there was an afterglow where the microwave background occurred 400,000 years later. Then there was, the universe was made of atoms, and there was nothing to light up the universe. So it's called the Dark Ages, even though it was lit up by the previous microwave background, which was really bright. But no new light was being created, or very little new light was being created then. The first stars appeared about 400 million years after that, as shown here. These stars formed into galaxies. The galaxies started bumping into each other, and we had the matter-dominated phase of the universe here. And only today, when we're about here, 13.7 billion years after the extrapolated Big Bang, we have lots of galaxies around. We have the Wilkinson Microwave Anisotropy Probe WMAP satellite, and our universe is once again moving into an era where there's accelerated expansion, where we're not expanding as if there was just regular matter everywhere, but there's actually a repulsive gravity that seems to permeate the universe that are pushing things away. In relatively modern times, the latest billion years or so, it's becoming evident. It was always there, but before it was just dominated by the matter. The matter was just everywhere. Dark matter or regular matter, like you and me, had much higher energy density than the dark energy does today. But now the dark energy has taken over by remaining constant, and the regular matter diluting because the universe is expanding. So the dark energy is taking over and causing an accelerated expansion. Okay, so the forces in the universe that we know about that are given clear names are gravity. You'll see in a future slide is the weakest force. It seems to be the most pervasive force, though. Everything that is mass experiences a gravitational interaction. It holds us onto the surface of the Earth. It essentially holds the Earth in the solar system. It holds our star, the sun, into the Milky Way. It holds the Milky Way together. It holds together clusters of galaxies. And if you get bigger than that, it has a major effect on superclusters of galaxies. But after that, the universe expands. And the expansion of the universe, which doesn't necessarily have to be a force. It could just be momentum of the universe moving away from each other, but we now know there is a repulsive force that dominates. Another major force is electromagnetism, so everybody is also familiar with that. Anyone who has a kitchen magnet, the magnetism holds your pictures to the refrigerator. There's electrons probably in your monitor that are being deflected. So electricity, you plug things in, so your iPod or your computer, your laptop are all powered by electricity. Electromagnetism is a much stronger force than gravity, but there are both positive and negative charges. So for instance, on the average, your average person you will find is generally electrically neutral. So gravity is more important in holding people to the Earth than electromagnetism. When you get down to nuclei are not held together by electricity and magnetism or gravity. They have too little gravity for gravity to be an important effect in a nucleus. If you think of a heavy nucleus, it has lots of protons and neutrons in it. So P, N, N, P, N. So here we have, usually it's drawn in a circle. They move around constantly. Here you have protons that don't generally want to be together if you just consider their electric repulsion. So how is it you could have nuclei like that? Wouldn't they want to just explode? Because they're all positively, and the electrons are going around the outside, right? So they're not helping much. So the reason is that there is another force involved. In fact, there are two. But the most important one for holding nuclei together is the strong nuclear force, much more powerful than electricity and magnetism. And it falls off exponentially, so it's not felt outside. There's another nuclear force that causes things like electrons to be emitted from neutrons called beta K. It's a weak nuclear force, and it doesn't really hold nuclei together, but it is now understood to be a separate force from from the strong nuclear force. So in clear terms, there are four discernible forces that we can easily tell. About 30 years ago, maybe, I might have my timeline wrong, it was realized that the weak nuclear force and electricity and magnetism could be described by the same framework, and that would even make predictions about other particles. And so those predictions came true, and it was realized that the electromagnetism and the weak force were all part of the same force, the electroweak force. Previously, way back in Maxwell's time, James Clerk Maxwell, late in the 1800s, it was realized that electricity and magnetism were really the same force. And if you were to move a magnet, you would get an electric current in wires. And if you were to move something with electric charge, you would get a magnetic field. And so they are very much related. It was then realized that photons, light, are essentially emitted whenever you move something that has an electric charge. That is electromagnetic radiation. So previously, electricity and magnetism were put together into electromagnetism. Now we know, within the past 30, 40 years, that the weak forces can be unified with that into the electroweak force. So that's about as far as we go right now. There are lots of theories floating around still that try to incorporate the strong nuclear force into the others. They're grand unified theories. And they make many predictions that generally, it's not that they're wrong, but they're currently mostly untestable. So there are different flavors of grand unified theories. Probably the hardest one to put into this altogether is gravity. But now there are several theories that incorporate gravity. Most of them are now known as superstring theories or M theories, and involve different things called bulks, which is some kind of space-time or branes. And so superstring theories are attempts to unify all the forces. However, although they require the most intellectual bravado, and the people who do the superstring theories are usually the most skilled in mathematics and are able to have other physicists and astronomers kowtowed by a single complicated equation. What you will see the other physicists and astronomers grumble when they're not around is that superstring theory is essentially right now recreational mathematics. There is no clear way to test it. Some claims that it's already tested because gravity is what it is don't impress a lot of people. Many times a falsifiable theory, as I said last time, is something that you can go and make a clear prediction that has never been measured before. And maybe there's another theory that says something like loop quantum gravity could say something else. Then you go out and you look at that and you see whether it was right. So superstring theories are too many of them to make a clear single prediction about things. So we just don't know. There is hope that superstring theories could be brought into the realm of the actual physical measurement. And then it would be really great because we would have a single mathematical framework that could explain all the forces. Superstring theories are essentially, instead of describing things as single particles, you describe them as strings. That used to be two-dimensional strings, but now you can generalize that to n dimensions. And these strings can vibrate, and these vibrations tell what mass the particle is. And can be quite complicated and can match up with other strings. But we don't need to know details of that. I don't even know too many details of that. Okay, so if we look at the age of the universe and the energy, so as you go earlier in the universe here, the average amount of motional energy goes way up. The temperature of the universe goes way up this way. And so at some point, you have forces that become the same because they're the particles that essentially create them are interchangeable. So if we go to an early time where electromagnetism and the weak force, the energy of particles is high enough, so at temperature enough so that they're not discernible, then you don't have to make a difference between them. If you go to a much earlier time, you can go to here where the strong force broke off at 10 to the minus 35. So this is about where we think inflation might have occurred. So I'll talk a lot more about inflation. So the universe became expanded exponentially at that point. If we go to an earlier time where gravity is important, some kind of super force of the Planck time, 10 to the minus 43, that's when all the forces might have been unified. But there could be strange things happening before the Planck time. There could have been extra dimensions. There could have been other forces that were out there that were then unified somehow. So we don't really know too much of what goes on. There could have been other episodes of inflation that we don't know about. There could have been bounces where things that used to be collapsing then started expanding. Okay, so this brings us to the different kinds of energy in the universe. So what kinds of energy are there, speaking generally? It has been broken up into essentially two types of energy using a phrase coined only 10 years ago. A dark energy is a type of energy that might be considered gravitationally repulsive. So dark energies involve, there are different ways you can create a dark energy in the universe, create a substantial amount of dark energy in the universe, none of which we think has a substantial amount of energy density in your room or part of your monitor. One is, well, let's go to the lightest kind, cosmic strings. So cosmic strings are not just little strings from superstring theory. These things are huge strings. It could be related. These things are huge strings that go through the universe. And if you were to go up to this, they have a lot of energy density in them. And they're very thin. But if you were to go up to one, you wouldn't really know it because it does not have a gravitational attraction to you. Unless actually you're moving relatively quickly, and then strangely it has a bit of a small gravitational attraction. But if you're just at rest near a cosmic string, you won't be attracted to it gravitationally. So it's sort of free energy in the universe that doesn't have gravitational attraction, assuming it's not moving. It is not known if cosmic strings exist. It is possible to see them, oddly enough, because not them directly so much as if they were in front of background things, and there's lots of things in the universe, you have a cosmic string, you would see a duplicate image of something right next to it. So one part of observational cosmology is looking out at things and looking for doubles and saying, ooh, there might be a cosmic string going through it. Or you can look for things that have sudden edges because there was a cosmic string that cut it off, and you would see the same map of space twice. This would look the same as that, but it would have a hard edge, assuming it was a straight string. There, it's all smushed, so you can't tell what's going on. So every now and then there's a claim that, ooh, we think we found a cosmic string. And if you look at any big plate of the sky, many times you can find two things that look similar right next to each other. But always, if you look carefully enough, they're always different. So many times what you're seeing is gravitational lensing by something else. So there are no observational known cases of cosmic strings. But they're the most claims that there might have been. The next strangest thing is something called a domain wall. So a domain wall is sort of dark energy that's not confined to a string, like in cosmic string, has the strange repulsive energy confined to a string. But domain wall, it's a big wall. That's a space. Let's see. Just make it it's a wall. And this wall is all energy density. It's microscopically thin compared to any other energy scale, distance scale in the universe. So if you were human, made of regular matter, and you were to go up to a domain wall, you would be repelled from it. So it is repulsive matter in a more general sense. Strangely enough, if you were to, this is really strange stuff. This comes out of general relativity, by the way. So this isn't demanded by string theory. So if you were to take a domain wall somehow, and you were to make it into a domain ball, you were to wrap it around on itself and make it into a ball, it would then act like normal matter. And you could drop it toward the Earth and it would accelerate just like anything else would. Like everything, no matter what it is, without air friction, anything dropped toward the Earth accelerates at the same speed. So it was a famous experiment from Galileo. There's a famous experiment on the moon where an astronaut dropped a hammer and a feather and they both hit the moon's surface at the same time. That's the equivalence principle, and it's true. It's even true of strange gravitational things like domain walls. So if you were to wrap it up, it would act just the same. But when you unwrap it and you make it really big and you go up to it, it's repulsive. Are there domain walls in the universe? You don't know of any. They might be outside of our visual horizon, outside of the visual universe. If one was inside, yeah, we might see it. It might be pretty obvious. It would affect the things around it in strong ways. Okay, the next is the cosmological constant, or just sort of uniform dark energy everywhere in the universe. So this was first hypothesized, as I mentioned, by Einstein way back in the 19-teens as a way of propping up the universe and stopping it from all collapsing on itself. And then after Einstein found out the universe is expanding, he said that was his biggest mistake. You don't need a cosmological constant, and he cut it out. But nowadays, with supernova cosmology and the distant supernovas being so far away, they appear so dim, they're so far away, and the evidence for an expanding universe from the microwave background and from the faintness of supernova, we again create an expanding universe by putting in a cosmological constant. It's a uniform energy field that is repulsive everywhere. So we're in it, and it repulses everything. And it repulses itself, which is why the universe is accelerating in expansion today. Now, there's still a few holdout astronomers and physicists who think that that doesn't really exist. And every now and then you'll see a paper published trying to explain things without a universal cosmological constant. And the truth is, we only know that this kind of dark energy exists locally. We don't know for a fact it exists early in the universe, which is why we're now trying to look at supernovae further out in the universe than ever before, gamma ray bursts further out in the universe than ever before, and more minuscule bumps in the microwave background with the next mission to try to find out if maybe there's some evidence that this dark energy that we think is constant now actually evolved in the past and was stronger or weaker. Which brings us to the next one, the strangest one yet that I've already mentioned, phantom energy. This is a hypothesized type of energy in the universe that increases its energy density as the universe evolves. So it's not only repulsive, it's increasingly repulsive. So right now, there might be, for all we know, the cosmological constant is phantom energy. And we have a little bit of phantom energy, in our bodies right now that's repulsive. But it's so little compared to the normal gravitationally attractive energy density in our bodies that we can just sort of ignore it. But let's say it's increasing its energy density, it's increasing its repulsive force. There will be a day in the future, if that's true, that the repulsive force of this phantom energy is stronger than the gravitational attractive energies. Well, actually, our bodies are held together by electromagnetic energies. Stronger than the electromagnetic energy of our bodies. And then, boom, we would explode. Sorry, that's that. And if this keeps going, everything in the universe would explode. And essentially, if you linearly extrapolate, the energy density everywhere becomes too much, and the universe essentially ends in what's called a big rip. Everything is ripped apart in a finite amount of time. Now, phantom energy is even more controversial than all of these other ones. There are claims that it's not, you can't have this due to different energy conditions in general relativity or energy conditions in other theories of gravity. But look, it's creating energy anyway, right? General relativity generally doesn't conserve energy. So the microwave background radiation has lost energy from what used to be gamma rays, and now it's microwaves, much redder energy. So where'd that energy go, right? So in general, so far as we can tell, there is no global conservation of energy. So there are different energy conditions, though, that people might try to hold. But phantom energy even ignores almost all energy conditions and just says, look, we don't know why. It's just increasing. And here's some equations that would say that it is. So phantom energy enthusiasts like to point out that the current cosmological constant measured for supernova cosmology has error bars on it and technically goes into the phantom energy domain. So they would say that it's possible the universe is made up of a significant amount of phantom energy, and we're only here so long as this phantom energy is small enough so it doesn't blow us up. These are the dark energies of the universe. Let's now go to what might be called, okay, this is so an APOD did a big rip, and this is just a cartoon because galaxies aren't made of puzzle pieces, a cartoon of a galaxy being ripped apart by the big rip in 10 billion years or so. Okay, let's now talk about another type of energy, light energies. These are gravitationally attractive. These are the kinds that we're most familiar with. Of course, the most familiar type is matter, and that includes dark matter. of which most of the universe, much of the matter that we know is there from watching galaxies, that doesn't light up. We don't know what it is. If it was made of people, it would glow in the infrared and we would know it. If it was made of stars like our sun, we'd know that. It's not. Maybe it's made of more dim stars, but probably not, because we're not seeing them in the halo of our galaxy. It's probably some kind of elementary particle. So there's elementary particles awash, and they might be moving through us all this time. It is not a dark energy, though. It acts gravitationally like we do, assuming it's actually running, moving slowly. So, meaning not as fast as the speed of light locally. So atoms, people are all made of this regular matter. This is the kind of stuff that we've been, studying. Most of physics is involved in that, I guess. All the other sciences are essentially involved in that, and radiation as well. So a different type of matter that is also light energy is radiation. So examples of radiation are electromagnetic radiation, light that we see all the time, neutrinos that are emitted from the sun, other exotic things that come out of particle physics, one of which is called an axion. So what most people don't appreciate is that this type of radiation, once dominated the universe and is more gravitationally attractive than normal matter. So it attracts, you can't use the Newtonian F equals gmm over r squared for radiation. No, that only works for slow-moving matter. Once things speed up near light speed, they're even more gravitationally attractive. So you would say that photons technically have so little matter in them that we essentially call it zero. So photons people call massless. Yet, things like photons can dominate the gravitation of the universe. So it's because that even though they have little of this, they've got a lot of this, and they're very gravitationally attractive. One of my proud moments is realizing that we're on a continuum here, and I popularized recently a different kind of light energy that could be called ultralight, which is even more gravitationally attractive than radiation. And just like phantom energy is all the types of dark energy that were not mentioned, ultralight takes up all the kinds of energy that is more gravitationally attractive than radiation. And we have no clear knowledge that these exist, and you can go into the early universe and put limits on them, but it is possible that there was part of the early universe that was dominated by a type of energy that was not matter, that was not radiation, that was not even any of the dark matters, that was an ultralight kind of energy. Okay. There is even stranger things. If you weren't happy with things that were sort of constant in their attractive and repulsive properties, there are energy fields. Sometimes the simplest kinds of these is called a scalar field. And typically mathematically modeled, scalar fields are supposed to be responsible for inflation. Now, why can't you have a scalar field is just something that, like temperature in your room. There is some temperature at every space. There's a single number. Where you are, it's a little bit higher because you're heating up the room, whether you want to or not. In the corner of the room, it's a little bit cooler. And you can put a temperature at every place in the room, and then you have a field of temperatures. And since there's one number that defines this temperature, it's technically, mathematically, a scalar field. Well, you can have energy density in this kind of scalar field. And it could be uniform, and it can do things like drive inflation, or cause relative gravity, or other things. And it's possible, so people point out, if that mathematics isn't complicated enough for you, why stop with scalar fields? We don't know that it would be necessarily a scalar field that would drive inflation. You can have vector fields. So just like a vector, which is velocity, as opposed to a speed, if you say something is speed, that's a scalar number. It's moving at, your car is moving at 50 kilometers an hour. But you can say, oh no, it's moving toward the center of town. And that gives you a direction too. So that's a vector. So you can have vector fields as well. So if we not only have, so what's an example of a vector field? So if you take every atom in this room, in your room, it not only has a speed, a temperature, but each atom has a direction that it's moving. And so that could be considered a vector field. You can even have tensor fields, and we're not going to get into that. Even more complicated. You can always make things more complicated. So why is it that a scalar field drives inflation? Because it's simple enough to mathematically model, and by Occam's razor, we just deal with the simple stuff. And if we can explain it that way, why bother coming up with something more complicated? But we don't know that a scalar field would drive inflation. It might. It's certainly the simplest field that might. And these scalar, vector, and tensor fields can have episodes, or they could be attractive or repulsive as they change. So they're even more complicated. And we're not going to get into them too much. Okay. Backing up a bit, going into the Big Bang, there's problems with the original Big Bang as it was hypothesized 50 years ago. One was the horizon problem, which is why is the universe so uniform? So if we look over toward the north pole of the Earth, and we put a telescope on the north pole of the Earth, and we look out at the microwave background, it has a temperature. And then if we take the same and we drag it to the South Pole, and we look out the South Pole, and we look at the microwave background, we find it has the same temperature. And the question is, how come those two are the same temperature? How do they know about each other? They used to be outside of each other's horizons, so that's called the horizon problem. Also, we find that the universe is either geometrically flat, so that volumes have 4/3 pi r cubed, or pretty close to geometrically flat. So why is that? That's called the flatness problem. And there's one I won't describe very much, is how come there's so few magnetic monopoles. So, okay, I'll describe a little bit. So there are monopoles of electric charge. A proton has sort of like that. It's positive. There's an electron. It's negative. But if you ever have a magnet, your refrigerator magnets, which we popularized earlier in this lecture, they're one pole on one side of the magnet and the other pole is on the other. They're dipoles. There's always two poles. So why don't you just divide that magnet in half? Get a big kitchen cleaver, just break it in half. Well, what you find is that doesn't work. You still then have two magnets, each of which are dipoles. So you could break it up into zillions of parts, and you'll just have lots of dipoles. No monopoles, no magnetic monopoles. So the question is, why not? Thinking is they might exist. So a classic solution to this is the inflation problem, is the inflation solution, which is now generally believed in cosmology. So that is that part of the universe where the universe begins to expand exponentially. So if you do that, you can take parts of the universe that used to be in touch with each other and can come to the same temperature, and then you can move them apart exponentially fast, faster than the speed of light, and they will end up far enough away so that when we look at different parts of the universe now, they would be the same temperature. So it solves the horizon problem. Let's see. The problem is that it has to be driven by a cosmological constant. So what caused inflation? There was some kind of possibly scalar field that had some kind of transition, possibly when the strong nuclear force froze out of the universe, when it became too cold for the strong nuclear force to be combined with the other forces. Then, as inflation ended, and this required a lot of mathematics that were worked out over the past 20 years, you can what's called reheat the universe and get back your atoms and molecules that were increasingly rare when the universe expanded exponentially in inflation. So here is a diagram which makes us feel good about inflation, where the universe used to be really small. And then it inflated, and now it's really big. And here's our standard universe picks up here after the inflation. And so this is as you go toward the present and in logarithmic axes. Here's another picture of it. So it shows the horizon problem. Since we're low on time, I'm not going to talk about this in big detail. We essentially saw this in previous. Let's see, low on time. So we did some of this theory of everything in order to go before the Planck time. Inflation occurred roughly at this time. Inflation ended at that time, where particles were recreated. The weak nuclear force froze out here at 10 to the minus 12 seconds as the universe kept expanding. Quarks combined to form protons around 10 to the minus 6, starting around 10 to the minus 6 seconds when the universe is 10 to the 13 kelvins. So right now in your room it's about 200 and some kelvins, so it's much cooler. 10 to the minus 2 neutrinos decoupled from the protons. So trying to explain all of this, possibly one way to do it is to have more than 3 spatial dimensions. So general relativity includes 3 spatial dimensions and a time dimension. Quite possibly, though, as string theory maps out and does better in higher dimensions, you can wrap up other spatial dimensions, and they rolled up. So they used to be, the universe way back had more than 3 spatial dimensions. But the dimensions froze out like forces did, and they rolled up to become really small. So if you try to go in those spatial dimensions, it's really, really hard for you to do it. An example of this is if you lived on the surface of a balloon that has 2 spatial dimensions, you might become aware of the 3rd spatial dimension that's in there, but if you tried to go, you'd have to break off the surface tension of the balloon and go in, and that's hard. So you can't do that. So we would have trouble moving in the extra spatial dimensions, and we wouldn't even see them unless we know exactly what to look for. Also, tension, equivalent of tension holds us to 3D. This is what's called a tesseract. I don't know if I'm spelling it right. A tesseract has been well known in mathematics. It is a 4-dimensional cube. It's a 4-spatial dimension cube. So here you're seeing sort of a rotation around that, and you can actually make a 3-dimensional projection of a 4-dimensional cube pretty easily. And so I actually did that once. It's kind of fun. So you can look that up on the web and do that. But this is a 4D cube and doing a rotation around it. This shows how string theory, if you have a 2-dimensional, can be shown as 1-dimensional, can be compacted into 1-dimensional. Here you have something that can be compacted into a string, a bigger one. Eventually you can have multi-dimensional surfaces. We just don't have a lot of time, and it's not real important. And string theory, as impressive as it is, the mathematically beautiful geometric theory sadly has little unique tests that say, here, this string theory is the one, go do this. Multiverses, okay, this is weird. So how do we know our universe is the only one that exists? Well, outside of our visible universe, there could be other visible universes that currently are causally disconnected from us, which means that we can't do anything that affects that other parts of our universe, and they can't do anything that affects us. Maybe in the past you were causally connected, which is why the microwave background is the same in different directions. But right now we've become disconnected. But people can create other universes well out there that are, it's like a balloon. You have a balloon, you have another balloon. So you ask, which direction in your balloon can you go to get to the other balloon, which is a causally disconnected universe? And the answer is there's no direction. Everywhere you go on that balloon just keeps you on that balloon. But if you had other spatial dimensions, there could be other universes out there. And since they're causally disconnected from us, there's no easy way to know about them. There's no testable way to find them. So we're moving into the realm of philosophy. So these could be disconnected. There could be arbitrarily number of spatial dimensions. It's very rare when you hear more than one time dimension hypothesized, though. Every now and then you will, but pretty much time, which is not well understood sometimes. There's a self-referential quote. Our universe, going out of philosophy, might be an oscillatory universe. It might there might be big bangs and big crunches. So, for instance, how can that be? Because we're in a universe that's expanding due to a repulsive. Well, maybe the dark energy of our universe will evolve. Maybe it will decay into some kind of energy density that's very, very large. Well, no, the energy density has to remain the same. So maybe it will decay into a flat universe that is made of regular matter, or even in some way so that even though it appears flat, our universe is slightly more dense than flat. And if so, we could have a big crunch in many billions of years where the universe recontracts on itself. And then maybe it bounces and you get a bang, crunch, bang, crunch. Maybe that's the way it works. Many worlds interpretations. So this says that every time that there's some kind of quantum decision, which could be one of your decisions, because maybe your brain makes quantum decisions. So every time you get a decision between left and right, and it's made in a random decision, and you choose left, maybe another universe breaks off where somebody chose right, to go to the right instead of the left. And so there could be however many quantum decisions there are to be made, there could be that many universes. And there could be lots of all of you out there who just happen to make a different decision. But you in this universe remember the decisions you made in this universe. And you're causally disconnected from those other universes now. But for all we know, it could happen. Again, the problem with some of these multiverses is we don't know really clear ways of testing this. At least no way has come forward yet that I'm aware of. So I did an APOD on this. Multiverses, do other universes exist? It might be, why is there an eyeball here? It might be in our own minds that this exists. Maybe they don't, that doesn't happen. Or maybe there are causally disconnected universes here shown to be soap bubbles that occur elsewhere. Ooh, the anthropic principle, another controversial principle in universe theory and cosmological theories. So maybe the only universes that exist with us are the ones that we can remember, in that sense that, let's say the universe had a really quick big crunch. We wouldn't exist in that universe, so we couldn't remember it. So maybe those things existed, but life like us couldn't have existed, so we can't remember that one. We can only remember universes that are able to create us. So that's called, essentially, the anthropic principle. And if you look it up on the web, there's different kinds of anthropic principles, but that's the simplest and most popular one. That we exist here because, because that's the universe that created us. And universes that didn't create us, they might have existed, but we don't know about them. Okay, here's back to this. So what we have here is a really small sphere, one of the smaller spheres yet created. And it's found that this sphere has an unusual attraction to plates. And it's also found that two plates that are held close to each other have an unusual attraction toward each other. And it's called the Casimir force, or the Casimir effect. And it's not really called a separate force because it's the nulling of forces that are electromagnetic or other things. So, but the Casimir effect causes mayonnaise to flow slowly because there are small particles in mayonnaise that are attracted to each other by this. So it's in everyday life. Micromachining keeps running into this problem because they make small things and they stick together. The Casimir effect actually can be repulsive at the same time. It's thought that quite possibly the Casimir effect is called by vacuum energy density. And it's thought that maybe the dark energy, the cosmological constant, is also a type of vacuum energy density. Instead of there being zero, vacuum being completely empty, vacuum has got lots of elementary particles that are being created and annihilated all the time. And maybe there's some reason that some of them don't exist, leaving a force. Why that would be, details of that, just not known today. So this effect, the Casimir effect, is hotly being explored in modern physics today, trying to understand it better and better. It might have a relevance to dark energy. It might give us insight into what dark energy is, whether dark energy can evolve, what would have created the dark energy, because we don't know what creates the dark energy, essentially the cosmological constant that is repelling in the universe today. Okay, and that will clear this lecture, but we've got more. We're going to go to the APODs for today, and then we also, after that, we have a, yeah, we're running fast on time. We have evaluations. Oh, which reminds me, let's go back to that and do the next one. Sorry, from current slide. There will be forms handed out for evaluation today, but also I think it's called ratemyprofessor.com. Now, I'm not advocating a particular website. I think there are other professor rating sites on there. So if you feel that you haven't been able to do it, you can go there and review this course there. Although here in Michigan Tech, the ones that matter, I think, are the in-class evaluations. Okay, so let's zip through this. You can read these. You don't have to listen to me. Recently found unusual auroras over the north pole of Saturn. What causes them? Well, it's particles from the sun, but what causes the auroras to change in seconds and pervade the north pole of Saturn, not really known. The International Space Station, has now been going for 10 years. Its 10th anniversary was on November 20th. So here you see a picture of the Endeavour space shuttle launching to go to the International Space Station. So I want to keep this short. This is a planetary nebula, M76, bright enough to be given a Messier number, yet not well studied. could be a sun-like star created that at the end of its life. Going to go a little annoyingly fast. Okay, here is an interesting picture of sunrise, sun, and moon in the same picture. All the way over here is the sun. Where is it? Here it is. Here's the sun. And then this 360 degrees panorama, or actually 180 degree panorama. Here's the moon on the other side, a nearly full moon. And this is in front of, where is the, Serene View takes in part of the longest bridge in Europe, the Vasco da Gama Bridge. And it's in Portugal. Okay. Okay, here is a star-forming region, the Cone Nebula. Here is the Cone Nebula. Why the Cone Nebula has its shape, not really clear, possibly related to winds coming off of a star that you might be able to track to the point of the cone. There's an open cluster of stars, and the Phosphor Nebula is here too. Some really interesting texture due to stars forming in this region. I recently announced that it is thought that there are actual glaciers under Mars. So earlier in this class, we talked about the Phoenix lander, which actually has just gone dead, seeing small sheets of ice near the North Pole of Mars. But here we see buried closer to the equator, under these equators, are big sheets found by radar of glaciers that are made of ice water, which might be important, surely important if astronauts are going to land on Mars in the future. They're going to want to dig in there and get water for them to drink because it's expensive to carry heavy, I mean not heavy water, but water that is a lot of mass up into space. Oh, this is something, a big buzz in the astronomical community. A big fireball was seen over south central Canada. And so here's a picture from a police cruiser. Here it is. So this is driving down the street. This is what the police cruiser camera saw. So here it is again. It's going to go, on the far side of clouds. And recently, it's been reported that pieces of this meteor, this possibly Death-sized meteor, have been recovered. So if there's enough videos of this, and I understand there's a lot, and they can see stars and get positions for where these are, they might be able to track this back to an orbit in the solar system, maybe even to a known comet, and then they can then track it forward and find pieces which they already have, and they might be able to recover pieces from a known solar system object without having to go there. Sometimes the universe comes right to you. This is the Horsehead Nebula in Orion, star-forming region. This is a dense molecular cloud that looks a little bit like a horse. I'm not going to do more on that. This is two galaxies colliding. This big galaxy is eating this smaller galaxy and causing it to look strange. Beta Pictoris, which has been known to have a bright star in the sky, known to have a dust disk for a while. Actually, a planet is now being claimed around it. Beta Pictoris b. In the morning sky, there's a conjunction, which is two bright planets appearing near each other. They are Venus, the lower one, and Jupiter, the higher one. So go outside and see that. Here's from the Apollo 15 program, a panorama of an astronaut exploring the moon. And here you can get a big feel for what it's like to be on the moon, including a lunar rover. Here you see a very massive cluster of stars, open cluster, in the Carina Nebula, and there's some unusual looking stars forming gas clouds, molecular clouds that are forming stars. Here you can try to find the astronaut on the space station. This is the Columbus module. This is a truss on the space station. Here are some solar panels, and the astronaut is here. That's the astronaut. Which brings us to today's. A few days ago, there was this conjunction, but the moon was there too in crescent phase, so it looked like a happy face. And this picture is taken from the Mount Wilson Observatory overlooking Los Angeles, and here are the skyscrapers of Los Angeles, as long as the fog that goes usually along with Los Angeles. And that takes us up to date, so we will do more APODs next week. And I'm going to sign off, well, not really too early so that we can review the class, so I will see you next week.